Aging it's really happening. It's going to be solved, I think, in the next. It's happening now. It's being solved as we speak. Trying to understand aging in a human being, well, biologists have just failed to do that over many centuries of studying it. So the current strategy is to say, okay, let's take a really simple organism, just the simplest organism that you can find, which is an animal and does show aging, and try to solve aging in that one organism. And if we can do that, maybe what we learn will be applicable to humans. In the organism that I work on, C. elegans, increases in lifespan of up to tenfold have been achieved.
One of the important things that people look for in the aging field are things called biomarkers of aging, things that you can measure tangibly over the course of an organism's lifespan. So, for example, what I work on, the things that I work on were originally thought to be biomarkers of aging. So that's little bright patches of fluorescence in the worm intestine. What I've shown is actually that's not a valid biomarker of age at all. What it is actually, it's much more a marker of death. So the more bright stuff a worm has, it's much more likely to die very soon.
The current working model is that organisms can actually regulate their growth and their aging rate according to how much food there is. What we're studying is this sensing system for nutrition, which is controlling aging and growth. And what our findings implies is that in principle we can manipulate with drugs this sensing system in order to produce increases in lifespan without having to reduce food intake.
We've got worms. When you shine a UV light on a worm, it just comes up blue. So I haven't put that there. That's just part of a worm. We think that the almost death of the worm kind of happens almost in the intestine. That this is almost like a heart attack that we're seeing. It's like some kind of trigger of death that once started kind of doesn't stop.
Aging is a trait like any other. It's a genetically controlled trait like any other, like eye color or hair color or whatever. What we try to do is to use very simple organisms that are very easy to work with in the laboratory and cheap to work with, to identify genes that control aging, and then to find out what those genes are and what they do. And there are reasons for optimism there, because remember that many of the genes that actually encode for the worm are the same genes that encode for humans. And in fact, some of the genes that control aging in worms are present in humans, and we've shown that those equivalent genes control aging in many other organisms, so in fruit flies and in mice, for example.
Look, you can see the brightness there, this is it, and you can see it's still alive, but it's just getting much, much, much brighter. That spread is death. That's showing the cells dying, and you can see that it completely consumes the worm. But can you see how bright that is compared to before? It's a real live death, as it were.
If aging was retarded in humans, what one would expect is a reduction in the levels of most or all aging-related illnesses. So you'd have a reduction in levels of cancer, reductions in levels of dementia, such as Alzheimer's, reduction in cardiovascular disease, reductions in type 2 diabetes, reductions in blindness, in osteoporosis, in incontinence, in all of it.